So in this lecture, I'll be raising the eye a bit from the raising the view a bit from the grasp patterns that I talked about before, and talk about architecture level and design patterns from the Gang of Four book. Um, Architectures, I'm going to go through two of them, the layered architecture style and the model view controller. And for design patterns, I'm going to go through a small selection of design patterns from that book. There are plenty more. If you look at the inside cover of the Gang of Four book, there's a long list of them and are categorized according to certain principles. So if you have a problem and you're looking for a way to solve it, well, you start by looking at the inside cover, and then you can go and read about the specific patterns from there. So the layered architecture style, this is a very common architecture style, and many of your systems are using it, even if you haven't thought about it as such. The problem is that you have a group of subtasks, and they depend on other subtasks at different levels of abstraction. So you have something which is perhaps high level, like the user interface, and you have other things which are more lower level. So from the user interface, you want to have overall business rules enforced. That's one. So the user interface is one layer, the business rules is another layer. Based on this, you may have even more detailed business rules and business logic. That's another layer. These in turn will perhaps connect to a database and have persistent storage. Well, database and persistent storage is another layer again. You do this in order to minimize connections between layers, or you try to do this at least, which means that at the top of each layer you will have controllers, to talk in the grasp terminology, that takes the input from whoever is calling this layer and orchestrates what's going to happen inside a layer. At the bottom of a layer you will have indirections, so you will perhaps have other classes that you call in order to shelter yourself from what may be going on in the next layer. So you have a small select input places where you can enter a layer through controllers, and a small select places where you can exit the layer through indirection classes. You make sure that each layer has clear responsibilities, so that it's easy to identify that this functionality is on this level of abstraction and therefore should be in this particular layer. So two examples of this. Let's start with the three-tier architecture. This is a very common architectural style, that you have a presentation layer. You have the logic layer that does all the business logic, everything that you want to do with whatever you get from the presentation layer. And then you have a persistent data storage layer. Many of your applications will implicitly have this type of architecture style, no matter if you try to get this or not. Even a web server. So you have the web pages stored, you have the web server that is responsible for serving the web pages. If you have logic on the server, if you're running Node.js, for example, this ends up, all that functionality ends up here. And in fact, compiling the actual web page that the customer or that the user see are then the presentation tier. And then you're running this in two levels. You will have half of this will be run in your web browser, and the other half will be run on the server side. So even if you're not explicitly have decided to use this particular pattern, you may very often use it anyway, implicitly. Another example that is often touted is the Windows 2000 architecture, where you have, going from the top, you have your user applications up here, where you can actually have both Windows applications and Linux or Unix applications, because there is a POSIX subsystem there. And the next level, you have user mode, and you have these different subsystems that are these are the APIs that you connect to. If you're running a Windows application, this is the Windows API. You have security and stuff here as well. As you notice, you don't have to have one layer, only one layer at one level. You can have many different. You can have, as you have here, OS2, POSIX, Windows 32, security, etc., etc. But the idea is that there should be very little connection between these layers, but more connection in the vertical direction. Going into kernel mode, this is more obvious because you have, well, kernel services, and they in turn use things like input-output management, process communication, virtual memory management, and so on and so forth. These in turn then connect to your kernel drivers and your hardware abstraction layer. So this layer is responsible for everything that has to do with the hardware and how to interact with your specific hardware, which means that everything above do not need to know what type of hardware you have. They're connected to the hardware abstraction layer that is then responsible for talking to your actual hardware. Each of these layers have their controllers at the top and may have these indirection classes at the bottom to shelter themselves from whatever happens underneath, which means that you could replace. If I want to have a different hardware, you can replace this hardware abstraction layer, and then you can run on a different type of hardware. Same thing up here. If you want to run a Linux application on your Windows machine, well, you replace the Windows 32 layer with a POSIX layer. Model view controller is also another very common pattern. So the thing is with these architectural patterns is that you do not use only one in your system. You can use many different at the same time. So your layered architecture can also be included inside a client-server architecture, for example, where you have your web browser as a client and you have your web server as a server that is then running a layered architecture style. Inside your layered architecture style, you can very well model it as a model view controller. The problem we're trying to solve with the model view controller is that we have an interactive application, and as such there are basically three main responsibilities. It's presenting data, it's managing the data, and making sure that it's consistent according to all the rules and regulations we have, and then we have storing the data. So if I'm making a game to play cards, for example, we can present the cards to the user in different ways. Managing would be the rules of the card game, and storing it would be keeping track of where the cards are, if they've been used, which pile they are in your game, and so on and so forth. So we divide the system into these three parts. We have a model that is your data store. The only thing that one has to do is to maintain your data, and that it's persistent and it's consistent and it's stored in a way that fits with the rest. You have view, which is presentation of data. You can have more than one view. If you look at an Excel spreadsheet, for example, you can look at the data in your Excel spreadsheet and you can make a number of different graphs. You can make a pie chart, you can make a line chart or whatever with your the same data. So you can have many presentations of the same data. Those are your views. And then you have controller, which strictly speaking should also handle user inputs, but above all should manage business rules. Why I say strictly speaking is because modern GUI frameworks sort of want to handle the user input as well, which means that you mix them up with the model. So you have model and the user input bit of the controller, but you definitely want to keep business rules into the controllers separately. We can actually use the same example for this, the three-tier architecture. We have our model, that's our database storage. We have our views, and we have our controller. So, that's so much about the architectural styles. Let's go down to a couple of design patterns from the Gamma Helm Felicitas Johnson book. Observer is the first one. The problem is that we have one object where things happen, and we want to be aware of what's going on. So in our point of sale system, for example, let's say that we want to whenever you add an item to the sale, you want to display that to the customer and to the cashier. But how do you know then that the sale item or sale object has been updated? Well, that's one place where we can start using our observer pattern. So what we have is that we have an observable. That's the entity that we want to keep track of. And we can add one or more observers. Those are the ones that are interested in being notified when things happen. So this, we have an abstract class observer, and we have this concrete class observable. This concrete class has a few methods. We have methods for adding and removing observers. Those are public. It's got a list of observers internally, and it's got a method called notify observers. So whenever something happens in my observable, I call the notify observers method. This one looks like this, something like this at least. Basically goes through the list of observers and call an update function on them. This update function is here, and it's abstract as well, which means I need to implement it concretely for my particular case, the display. If you've programmed in Java with the Swing GUI framework there, you know that you get action listeners and you get event listeners, and they work very much like an observer pattern. So you have a button, which is observable, it's over here, and you add an action listener, which is yourself as an action listener abstract interface. And when you click the button, you get an action event, and you get the event sent as a parameter, which means you can investigate, all right, what about this event? Which button is clicked? Do I need to worry about it, etc., etc. You need to actually send some handle so you know what happened, because you can be an observer to more than one observable object. So if I'm the main GUI class, for example, I have many buttons. So how do I know which button was clicked? In this case, maybe the display is connected to many different sales at one time. I don't know why, but let's say they are. Which means I need to know which sale was updated. And that's covered by passing yourself. You pass this pointer to the update function, or some other object that embeds a link to what actually happened. The problem with this pattern, if you do this in C++, that's not a problem. But if you do it in Java, so you're extending a concrete class here, which means that suddenly you cannot extend anything else. If this was your user interface, maybe you want to extend JFrame. If you're a member of some other class hierarchy, then suddenly you can no longer inherit this observable. This one is okay because it's abstract, so this is just an implementation of an interface. This one is trickier, since Java doesn't support multiple inheritance. The solution is actually, so the observable exists in the standard API in Java, but it's very difficult to use them for this particular reason. And the solution that I've seen which is most common, is that you re-implement all the methods of observable. It's not that difficult to do. If we go back again, it's 3 methods and 1 vector full of observables. So it's not difficult to do. It adds like 20 lines of code to your program, including whitespace. And that appears to be the best common practice to do this in Java. I tried to look into if I could do it with inner classes and such things, and I probably can, but it's more hassle than just re-implement the methods, which, as I say, seems to be the common practice to do that. One other problem is that you may want to observe multiple observables. As I said, you may have to keep track of different sales, you may have to keep track of different buttons in your user interface, and so on. And this is true for C++ as well, for that matter. You can, of course, you get an event and you can do a giant switch case statement. Is it that button that was clicked? Is it that button that was clicked? Is it that window that was updated? Is it that data store that was updated? And so on and so forth. We can use inner classes, private inner classes, which is supported in Java. We can use anonymous inner classes, which is also supported in Java. I don't know if this is covered in C++11 or not. We can use Lambda functions, which is new and fancy in Java, and in my mind, I learned about Lambda functions from Lisp, and they are really elegant and really useful. They look a bit clunky to me in Java, but there you have it. So if we were to do this concretely, here's how we would do it in Java. Inner classes, we create a private class inside our main class that implements my observer, so that I get I override my update function here. So if I want a dictionary observer, well, this is the one, but this means that I only get this update method is only called from the dictionary, because that's where I add it. So here's my dictionary, and I add myself to that one. So this method is going to be called as a dictionary. This update method is going to be called whenever something happened in the bannerad class. So that's one solution. Create a private class and then put the update function. In this case, I could have done it with simple standard update functions inside, because I have two different classes. I've got a bannerad observable and I've got a dictionary observable. But if both of these were buttons, for example, in the user interface, they would have the same signature, update button clicked. That way, for that reason, I would need to have a private class for each of them. Next step is similar. It's just one step up in terms of I don't have to find a good name for them anymore, because I can, let's see, where do we have it here? I do an abstract or an anonymous inner class here, where I override the update function. And then I do all the logic for whenever I should click on, whenever something happens in the dictionary. I can do the same thing for the bannerad class here. I haven't done it because I was lazy. This makes it, well, if it's complex behavior that you want to happen here, well, you would call a method for it here. But the good thing is that you can adhere to the generic interface, that there's an update method, which means that the other side don't have to know what you call this logic method inside your class. They only know, as they should, that there's an update method. Because you are a dictionary observer, you have an update method, so I'll call that. And then you can call your own methods in here. You would want to do that to keep the initiation method shorter. Otherwise, you have all the logic here, and then you have all the logic here, and then if you've got a few more buttons, you've got a method or a constructor which is more than a couple of 100 lines long, which is never a good idea. The third alternative, I think they introduced this in Java 8, is to use a Lambda function. And how this works, this is magic to me. The syntax here is completely opaque. You have no idea what's going on. But you create an anonymous function that takes one parameter, a dictionary, or a dictionary observable, I presume. And inside this anonymous method, you basically, in this case, I just print out something. And it just so happens that the anonymous, or the method, or sorry, the parameter I got is usable inside this very anonymous and very ugly method. So I'm including this here. You'll have to read up on Lambda functions in Java yourself if you want to know the exact syntax for it. It just looks ugly and clunky to me, but there you have it. So those are the three alternatives I have. I would go with either having inner classes. This is the one I've seen most of the time, because this is the one which is supported by the oldest versions of Java. It wasn't available in Java 1. Whatever, but of course, but it's been supported longest at least. So either having inner classes like this or anonymous inner classes. That's how I would do in order to get support many observable items in one observer. Singleton. Well, a singleton class is a class that can only exist in one instance in the system at any point of time. I can use this in order to limit access to certain resources. For example, I've only got one audio output perhaps in my system, so I can have one object responsible for audio output. And no matter where I am in the system, if I want to do our audio output, I call the same object, and that object is responsible for keeping track of that. There's a queue of audio to play, whatever. Same thing if I've got a data storage, I may want to have one entry point. Data storage is usually easy to, or usually supports concurrent access, so it's not as needed there. But let's say I have a serial port you want to communicate with, then definitely you want to have a singleton there, so only one entity in your system can communicate on the serial port, and that's responsible for keeping track if you have many places in the system trying to call the serial port at different points in time. So what we do in order to ensure this is that, first of all, we make the constructor private, which means that only members of the singleton class can now create instances of this class. That's a little C++ trick that you're allowed to do this. And then we have a method called getInstance, which we declare as being static, which means something in C++ and something completely different in Java, so don't confuse the two. Static means that it's available even on the class level. I don't have to have an instance of the singleton class in this case in order to be able to call this method. In this getInstance, I basically check if there is an instance of myself already. If there isn't, I'll create a new one. Otherwise, I'll return the instance that is available. And I keep that one also as a static variable inside my class, so no one else can access it unless I give it to them via this return statement. So whenever I need an instance of this class, I'll just call singleton class.getInstance and or : getInstance, and then I'll get the instance that I can use. That's the code, and if I were to model it, I can specify with the help of a stereotype that this is a singleton class. I've got my instance, I've got the getInstance method, which is public, and everything else is private here. Strategy pattern. So you have many different ways of doing the same thing, depending on, whatever, it can be, of course, different in your systems, but depending on your state, depending on the role that you currently have, depending on some setting or whatever, you have to choose between different ways of doing the same thing. And the solution here is to use polymorphism, which was listed as a grass pattern, but which is a standard, very basic object-oriented principle. On the high level, this is how we do it. So we have a context in which we want to do something, and we call the do your stuff method in this abstract interface. So the context only has a link to the abstract interface. And then we have the concrete strategies for how to do things down here. So when we instantiate this system and when we create the object, we will do this either as a concrete strategy A or a concrete strategy B and give that to the context. But the context thinks it's got a strategy and it doesn't care which instance it is, which means that the context is much cleaner, doesn't have to keep track of why I've got a different, why it's got a different way to execute things. And we leave that to some creator or something. And then you have your different strategies, which means that you can also extend them. You can create a new strategy here, and you only have to change in one place where you actually select which strategy to use. Everyone else, the context here, and everyone else that might use the same strategy, just uses it without knowing which subclass it is that they're using. Spell check is a concrete example. You can have English, you can have Swedish, you can have Lodgeban if you like. And your word processor doesn't need to know which spell checker you're using, because once you've created it, all it has to know that there is a spell checker that can spell check my document. And state, since we've talked about state patterns or state diagrams in the class, this is actually one way of getting them back into the fold of object-oriented design and UML again, and unified process. So if you have a system that you have modeled in your state diagram and you know that, all right, these are very important states in the system, this is actually a fundamental principle for how the system works, is that I have these states and I have these transitions between those states. This means that you would want your class diagram or your classes to mimic this structure or and mimic these states and state transitions. And you could say this is just a special case of a strategy pattern. But there you have it. It's got its own name at least. So if we look at the example, this is an example I've used before, where we're doing a model of a Pac-Man ghost. I had to look if it was Pac-Man itself or Pac-Man ghost. We've got the states hunting, eating, running, being eaten, and the respawn pattern or respawn state. And we want to do our system, we want to implement our system to mimic these, because these are very important states. This is actually how we want the ghosts to work. So, what's happened? Oh yeah, thank you. So we've got the ghost, and the ghost knows the current state. And then whenever it gets a chance, it'll call a do state. It might do that on every clock cycle, or once every time Pac-Man does something, I'll do the do state. And then I've got events like I meet Pac-Man, Pac-Man eats a candy, and so on. These mimics the event from my state chart. And I've got my abstract state. I've got the enter state, I've got the do, and I've got exit state. These mimic the entry and exit and do keywords I've got in my state diagram. So entry, which means do all the things that you should do when I enter the state. Do means do these things while I'm in the state. So when in the do state method, it's the do method I'm going to call. And an exit, when I exit the state, these are the things that should be done. And I'm not sure this is actually part of the official pattern, but it makes better sense for me to have it here. So if I am in one particular state, that state is probably the best entity to know where I can go from there. So if I am in one state and an event occurs, the current state is, again to speak in terms of the grass patterns, is the information expert on what can take me out of this state. So I put that into the interface here. And of course, all these different states then inherit and extend and actually implement all of these methods. I was lazy. I didn't put this into the model here, but I probably should have. So I've got my hunting state, I've got my running state, I've got my eaten state, I've got my respawn state, and I've got my eating state. All of them implement the enter state, the do state, or the enter state method, the do method, and the exit state method, and the get new state method. I've also been lazy, so if I shouldn't do anything, if I should remain in my current state when based on a particular event. Not all events means that I actually need to transfer into a new state, of course. Not all events are relevant for all states. So if this event isn't relevant for this particular state, I'll return null, because it's easy to detect. So when I get an event, what I'm doing is that I'm checking with the current state. Will this put me into a new state? If not, I'm done. If I get a new state, well, I call the exit state to do all the things to clean up from the current state. I set my current state to the one I got, and then I call the enter state method to do all the things I need to do in order to enter the new state. You notice one thing, that state transition events or actions, event actions, aren't modeled here, so I will need to find a way to put that in as well. They are actually not part of the official state pattern if you look into the Gang of Four book, but they probably should be somehow. I guess I would put that as some sort of aggregate here with all the same thing, using a strategy pattern for the transitions that can happen and the arches between the states. Anything more to say about this? Well, that's about it. Okay, abstract factory then. So you have different ways to initiate the system depending on the context. Let's say you can choose between different GUI frameworks. You can choose whether you want to use OpenGL and DirectX. You can have a command line interface, but you still want to have it looking like your GUI interface or whatever. So this is similar to the strategy, but it's focusing on the creator, on the creating side. We have a factory. This one is abstract. And the application, so everything else in the application only knows that I have a GUI factory in this case. They don't know which exact specific factory that they have. They have a handle to a GUI factory, and whenever they need a button, for example, they'll call the create button function, create button method. And again, they get a button, which is also abstract. It's also an interface, because you'll have concrete implementations depending on which, in this case, which platform you're in. So you can use the same system. You don't have to recompile it or anything if you're on a Windows platform or on a Mac platform. You probably have to recompile, but you don't have to exclude things and include things and use different build scripts. You can let the application take care of it. So somewhere in the initiation of this application, I have created a Windows factory or an OS X factory and put that into the GUI factory attribute that the application has. That's all the initiation I need to do. One creation of one specific subinstance here. They are in turn responsible for creating. So when I call the create button method, The Win factory will create a Win button. The OSX factory will create an OSX button. But all of that is internal to these concrete factories. For the rest of the system, they know that I've got an abstract factory, I call the create button, and I get the right button magically. I don't have to worry about it. This decreases coupling. This increases coherency, and because there is just one place in the system that needs to know which particular platform I'm sitting on, and the rest just follows automatically. So that's good with the abstract factory pattern. All right. That was all I had to say about the design patterns from the Gang of Four book. These, the ones I've mentioned here, the ones I've brought up, first of all, I think these are the ones that you'll find in the Larman book as well. Second of all, these are the most common ones. These are the ones that are going to be most useful for you. In the lecture, that's what you saw on the next slide, actually, I will be going through how you can use these patterns for particular contexts in when you're building an application. I'm going to use again the Pac-Man game as an example, but that's for the lecture.